Hi everyone! Salamat sa inyong patuloy na ginagawang pagsubaybay dito sa ating discussions about mechanics of deformable bodies. At ang ating magiging topic for today is all about stresses in beams. So before we start with our discussions, ay puntahan muna natin itong simple definitions of what are stresses in beams. Okay, pag sinabi nating stresses in beams, these are the stresses that are caused by bending moments. Sometimes they are also called as flexure stress. And the relationship between this stress and the bending moments are expressed in terms of the flexure formula. At ang ating magiging paraan ng discussions ngayon ay pakikita natin kung paano ang derivation ng stress formula, and from there we shall show an example of how to use the stress formula in dealing with beams that are subjected to bending moments. So let us have here our derivation of flexure formula. Let's start with a simple beam that is simply supported or supported at the ends by a hinge and a roller. And imagine that on the beam we consider two adjacent sections AB and CD. The two sections are very close to each other, and the distance that separates them shall be treated as d sub x. Imagine that this beam is subjected to a concentrated load P. Hence, due to this concentrated load P, the beam will be subjected to bending. And most probably, with exaggeration, this is what will happen to the beam after it has been subjected to the bending load. So, pakita ko lang uli ha. So, here is what will happen. The beam will concave in this manner, okay? So, and because of this concavity, the beam will be subjected to what we call flexure stress. So, mapapansin natin that after the beam has concave, the section AB and section CD rotated with respect to each other by an angle that is very small. We consider this angle to be d theta. Due to the rotation of AB and CD with respect to other, the following can be observed. We can observe the following. That the fiber AC, this fiber AC on top of the beam is shortened. There is shortening on AC, and by the principle that we have learned, we will expect that this fiber is subjected to compression. While this fiber at the bottom of the beam is lengthened, and therefore we would expect that this BD is subjected to tension because of the elongation of the fiber. And you will find that somewhere between AC and BD, there is a fiber EF. There's fiber EF somewhere here. That is not change in dimension. There is no change in dimension. The dimension remains unchanged, and therefore we would expect that EF is not subjected to stress, or stress in that particular fiber is equal to 0. And the section that contains this fiber EF that remains unchanged is what we call the neutral surface of the beam. We call this as the neutral surface because such surface contains the stress that are unchanged, and therefore they carry no load. And this neutral surface is the dividing section of the beam, so that the upper portion of the beam is either subjected to tension or compression, while the lower portion of the beam is subjected to the opposite stress, and from which the radius of the curvature also is measured, and normally the radius of the curvature is given by the symbol rho. Now, if you are to draw line C prime D prime, which is parallel to AB. So here is our AB, and imagine that we will be drawing a line that is parallel to this AB passing through F. You will find the following. If this will be the line that will be drawn, and imagine that this is our C prime D prime, we will see that, okay, this fiber AC is shortened by the amount C prime C prime, while the fiber BD, this fiber BD, is elongated by an amount D prime D. And the angle that this C prime D prime is making with respect to CD is also the same as the angle of rotation between AB and BC. This angle that is very, very small is also the same as this angle. That angle will be also this angle, d theta. Now, let us imagine that we consider a typical fiber GH somewhere at a distance y from the neutral surface. Imagine that we consider this fiber GH located at y distance from the neutral surface. Then we would expect that this fiber GH will have a deformation HK. Okay, HK, this deformation, the one that is shown in blue. And this deformation HK can be expressed by the relation between its position from the neutral surface y and the angle d theta that is subtended by that deformation. Hence, this arc length HK, which is the deformation of the fiber GH, shall be equal to the product of y multiplied by d theta, where d theta is expressed in terms of radian. Now, after which, we can say that we're to solve for the strain on the fiber GH. The strain being defined as the ratio of the deformation to the original length. Having shown that deformation is equal to the product of y multiplied by d theta for this fiber GH. Therefore, the strain shall be equal to the product of y multiplied by d theta divided by GH. But GH is equal to EF, as shown in this illustration. This GH is also equal to EF, and EF is equal or can be computed as the arc length that subtends an angle d theta on a radius equal to rho, and therefore EF will be equal to rho multiplied by d theta. So that if rho multiplied by d theta will be substituted to GH in this strain formula, therefore our strain will be equal to the ratio of the deformation over the original length equal to y multiplied by d theta over rho multiplied by d theta, and from this d theta will both cancel each other, and what will remain is the strain equal to the product or to the ratio of the distance y over the radius of the curvature rho. Now, if the beam will be assumed to be homogeneous and that it will obey Hooke's law, which says that within the proportional limit, the stress is directly proportional to the strain. Therefore, we would say that the stress shall be equal to the product of the proportionality constant, which is equal to our modulus of elasticity multiplied by strain. And if strain will be substituted with its value equal to y over rho, therefore the formula for stress will become equal to E multiplied by the quantity y over rho. Now, if we're going to consider isolating the left part of the exploratory section AB, here is our AB, and let us imagine that this part that I have given emphasis or mark shall be isolated as free body diagram. Let us try to isolate it here, and let us try to find out that this is our isolated view of the segment, the left part of the exploratory section AB. Here is our neutral surface, and this part shall be our beam cross-section representing this side. Imagine that the beam cross-section shall be drawn here, so that we shall be having our beam cross-section, and its width will be equal to this width. And the intersection of the neutral surface and the cross-section of the beam shall be called as the neutral axis. In this particular section view, you will find that the neutral axis shall be the line that will be drawn horizontally in this direction. Now let us imagine that on this isolated view of the beam, we consider a differential area dA. Okay, that from that section we consider a small area having a dimension dA that is located at a distance y from the neutral axis. It is our dA, okay, and that dA is located at distance y from the neutral axis. Okay, because of the bending, okay, and as reflected by the elongation hk, we would expect that the lower portion of this beam is subjected to a tensile stress, and hence this differential area will be subjected to a differential force dF, which is very, very small, as it is acting over a very, very small differential area. And the magnitude of this differential force will be equal to the product of the stress multiplied by that differential area. So that if we are to consider the moment resistance or the moment capacity of this differential area, therefore it will be equal to the product of y multiplied by that differential force. So from here, we can find that the resisting moment about the neutral axis of that differential area that is located at y distance from the neutral axis being subjected to a differential force dF, and whose magnitude is equal to stress multiplied by the differential area. Therefore, this would offer a resisting moment equal to the product of y multiplied by that differential force. And that resisting moment that this is offering is also very, very small, okay, because the area is so small. But if you are to consider substituting the value of the differential force, which is equal to the stress multiplied by dA in this formula, therefore our dm shall be equal to y multiplied by the stress multiplied by dA. Now, if we are to consider the total resistance of the entire section, hence the total resisting moment about the neutral axis of the entire area, which must be equal to the total moment acting at that section, is the sum of the resisting moments of each of the differential area. So if we will be adding all the differential moment that each of the differential area can offer, therefore that would be the total resisting moment of the entire area. And in design, that resisting moment must be equal to the actual bending moment acting at that section. Hence, we say that the moment which is equal to the resisting moment is equal to the integral of y multiplied by the stress multiplied by the differential area. However, a while ago, we just have expressed that this stress is equal to the modulus of elasticity multiplied by the strain. And if strain is substituted by y over rho, therefore, we shall have the stress equal to E multiplied by y over rho. Now, if this stress will be substituted in this formula, this stress is substituted here. Therefore, the moment will be equal to the integral of y multiplied by the quantity A multiplied by y over rho multiplied by dA. And if we will be rearranging and placing all those constant out of the integral sign, E and rho being constant, therefore we shall have here the moment equal to E over rho multiplied by the integral of y squared multiplied by dA. And I would like you to take a look at this term. I would like you to take a look at this term. In here, the term that is represented by the integral of y squared dA represents the moments of inertia of the section of the beam with respect to the neutral axis. And normally, they are denoted with the symbol I. So that if this I will be substituted to the term that is equal to the integral of y squared multiplied by dA, then the equation will become simplified to be m equal to E over rho multiplied by I. But a while ago, we have just shown that stress is equal to the product of E multiplied by Y over rho. And if this equation shall be divided by Y, therefore we shall have stress over Y equal to E over rho. Now, if this E over rho that is equal to stress over Y is substituted in this formula, therefore, our moment becomes equal to the stress over Y multiplied by I. And if this shall be rearranged, and then simplified and then solved for the stress, then we shall be getting a stress equal to my over I. So this is the relationship that shows, this is the formula that shows the relationship between the stress, the bending moment, and the fiber, the location of the fiber where the stress is being computed. So from this stress formula, so we call this as the flexure formula, and this stress formula represents the stress at any section of the beam on a fiber located y distance from the neutral axis. So from here, we say that Am is the moment at the section of the beam where the stress is computed. Y is the distance of the fiber from the neutral axis of the beam cross-section. And I is the moments of inertia of the beam cross-section with respect to the neutral axis. Now, for the maximum flexure stress, we say that maximum flexure stress on a beam occurs at the section where the moment is maximum and at the fiber that is farthest from the neutral axis. Meaning, we can expect the maximum stress to happen or to occur at a point or at the section of the beam where the moment is the maximum and at the position where it is farthest from the neutral axis of the beam. Hence, for the formula for the maximum flexure stress, that if we will be substituting the maximum moment to the m and c for the maximum value of y, therefore the stress can be written as mc over I, where in this formula c is the farthest distance of the fiber from the neutral axis. Now, let us try to consider having a beam that is rectangular in cross-section. Suppose that our beam is rectangular in cross-section, having dimension of width equal to b and a depth equal to d. So that we shall have here our beam cross-section. Here is our width, and here's our depth, defined by the distance. The neutral axis of the beam is defined at this located at this position at distance d over 2 from top or d over 2 from the bottom. And for this beam cross-section that is rectangular, the moments of inertia of the beam with respect to the neutral axis is equal to bd cubed over 12. And so if this will be substituted in this formula for the stress, we can find for the maximum stress of the beam, that is rectangular in shape, to be the moment or the maximum moment multiplied by c, which is equal to d over 2, and the moments of inertia, which is equal to bd cubed over 12. So in this relationship, d will cancel, 2 will cancel with 12, and that becomes 6. And so we shall have here the stress formula for the maximum stress in rectangular beam equal to 6m over bd. And that gives us our stress formula. Now, for us to be able to understand this concept that I have just presented to you, let us have this sample problem. Imagine that we're given the beam that is loaded as shown. So that for the beam loaded as shown in the figure, we are required to find for the maximum flexure stress developed, and the stress developed at fiber 50 millimeter from top of the beam, 3 meters to the right of the support at A. So we are here given the beam cross section to be 250 millimeter by 400 millimeter. And in this particular case, we are asked to solve for the maximum flexure stress and the stress developed at the section 3 meters to the right of the support, 50 millimeters from top, meaning we are finding for the moment at this particular section of the beam 3 meters and at certain distance, which is 50 millimeters from top of the beam. So how do we solve for the problem? So since we are looking for the maximum stress, therefore we will be needing to find for the maximum bending moment. So it is good to consider solving for the magnitude of the reaction at the support, and from there we try to draw the shear and moments diagram. So let's start with solving for the reaction at the support. Maybe we can start with solving for the reaction at A by taking moment at C. So that when we sum up moment at C equal to 0, considering that counterclockwise moment is positive, therefore we shall be able to solve for A. Now, because the beam is subjected to a uniformly distributed load and a uniformly varying load, therefore we try to consider identifying the magnitude of those distributed load. For this uniformly varying load, the intensity of the magnitude of this triangular loading will be located at this point, having a magnitude of 1/2 of 3 multiplied by 12. And it will be acting at a distance 1 meter from the right support. And so from here we can apply our moment equation so that 1/2 of 3 multiplied by 12 multiplied by 1 being the moment at C, while this one would have a resultant equal to 10 multiplied by 60 and a distance from the left support equal to 6. So that if this will be added here, I will have plus 6 multiplied by 6 minus RA multiplied by 9 equal to 0. And so from here, we can solve for RA equal to 42. And so this RA will be equal to 42. So after we have solved for RA, we can solve for R sub C by summing up moments about RA. So that when we sum up moment about RA equal to 0, considering the same direction, clockwise, counterclockwise as positive, we can solve for R sub C here. So that we solve for the counterclockwise moment due to R sub C. So I have here R sub C multiplied by 9. This multiplied by 9. This the resultant of this rectangular load will have a distance of 3 from A. Therefore, I will have minus 10 multiplied by 6 multiplied by 3. While this one would have a moment arm of 8 from A. So we'll have here minus 1/2 of 3 multiplied by 12 multiplied by 8 shall be equal to 0. So from here, we can solve for R sub C equal to 36. So after solving for R sub C, we can take that R sub C here to be equal to 36. So after we have solved for the reaction at the support, maybe we can now draw for the shear and moment diagram. Let's start drawing first for the shear diagram. Let's try to find the moment, the shear at every change of load position, A, B, and C here. So that here is our shear diagram. Let us consider our controlling points A, B, and C. So if we are to solve for the moment by the relation, we would expect that so the moment at the shear at the left of A shall start at 0. So meron tayo ngayon ditong 0. Therefore, the shear at the right of A will be equal to this concentrated this load plus the concentrated load at A, which actually is equal to 42. So when this will be substituted, I will have here 0 plus 42. Therefore, the shear at the right of A will be equal to 42. And this 42 will be somewhere here. Therefore, okay, this will be connected by a load, a line that is directed upward, representing this concentrated load upward at A. Then next we have to compute for the shear at B. The shear at B will be the shear at the right of A plus the area of the load between the right of A and that of the point B. And in the illustration, we see that the load between A right and B is actually a rectangle having a magnitude of 10 multiplied by 6. Therefore, if this will be substituted, meron tayo ngayong 42 minus 10 multiplied by 6, and that the shear at B will be negative 18. And negative 18 could be somewhere here, okay? And this will now be connected by a straight line because we have here a horizontal load representing degree equal to 0. Therefore, since the degree of the curvature of the shear diagram is always 1 degree higher than the degree of the curvature of the load diagram, therefore we would expect that the shear diagram between the A and B would have a degree equal to 1, and that will represent a straight line. Therefore, 42 and 18 here, negative 18 here, can now be connected with a straight line that runs in this direction. Okay. Then afterwards, we can now compute for the shear at the left of C. The shear at the left of C will be equal to the shear at B plus the area of the load between B and C. And the area of the load between B and C is rectangular, having a magnitude of length of having a base of 3 and a height equal to 12. So if this will be substituted here, therefore the shear at the left of C will be negative 18 minus 1/2 of 3 multiplied by 12, and this gives us a value of negative 36. So somewhere here we have a negative 36 value, and we can connect the 2 points 18 and 36 with a curve that is equal to a second degree curve because the load is a uniformly varying representing first degree curve. Therefore, it will be connected with a second degree curve that runs in this direction. Okay, this will be running in that direction. And therefore, finally, the shear at the right of C will be equal to the shear at the left of C plus the concentrated load at C, and that gives us a value equal to 0, and that gives us a value equal to 0. And this now becomes our shape of the shear diagram. Now, after we have drawn the shape of the shear diagram, we can now compute for the position where the shear is 0 because we would expect that moment will be maximum at the point where the shear is 0. And we will notice that on the diagram, we have seen this point where the shear is 0. Therefore, we have to consider what will be, where is this position, either from A or from B. And let us imagine that this distance be measured as x from A or s from B. Therefore, and you would find that there will be two triangles that are similar. And so from the similar triangles, we can solve for s and x by using ratio and proportion. So that using ratio and proportion, how do we express the ratio and proportion? I will have here 42 is to x, this is to y, the vertical is to the horizontal as 18 is to s, 18 is to s. But we expect that we are going to look at the relationship between x and s, because the sum of the two is equal to 6, therefore s will be equal to 6 minus x. And if this s that is equal to 6 minus x is substituted here, then we can find that 42 over x is equal to 18 over 6 minus x. And so from here we can solve for x, and that we can find that x is equal to 4.2. This x will be 4.2. With x equal to 4.2, then s will be equal to 1.8. And so you can find that this one will be equal to 1.8. So let us now draw the moment diagram from the shear diagram that we have computed. But in drawing the moment diagram, let us give emphasis on the magnitude of the maximum value and the moment at the section 3 meters to the right of A, because these are the moments that we will be using in solving the questions. For the part 1, we shall be working on the maximum stress. Therefore, we will be needing for the maximum value of the moment. While on the second part, we are considering the stress at a particular section which is at 3 meters to the right of A. Therefore, we shall be solving for the moment at that section. So let us now try to start our moment diagram here. Here is our moment diagram. Let us try to consider those change of load positions, point A, B, and C. And because we have additional point here, let us call this point D. And on the moment diagram, it's very important that we consider that in the computation of the moment diagram. So our moment at A will be at 0. Okay, will be at 0. So we consider this as our A moment. Then the next point that we shall be working is the moment at point D. And the moment at point D will be equal to the moment at A, okay, plus the area of the shear diagram from A to D. And the area of shear diagram from A to D is in the form of a triangle having a base equal to 4.2 and a height equal to 42. Therefore, our moment at point D will be 0 plus 1 half of 4.2 times 42, and this will give us a value of 88.2 kilonewton meter, and that value could be somewhere here whose magnitude is 88.2 kilonewton. So how are we going to draw the curve that will connect point A and this point on the moment diagram? Because we have here the degree of the curvature of the shear diagram, which is equal to 1. Therefore, we shall expect that this will be a second degree curvature having slope at this point of point equal to 0, and therefore we shall be expecting a second degree curvature that will concave in the downward direction. And so here is our curvature. The next point that we shall be working is the moment at point B, where the moment at point B will be equal to the moment at D plus the area of the shear diagram between A, B, and D. And in this case, we have here a triangular area having a base equal to 1.8 and a height equal to 18. Therefore, our moment at B, when those values shall be substituted, will be equal to 88.2 minus 1 half of 1.8 times 18, and this gives us a value of 72 kilonewton meter. So 72 kilonewton meter will be somewhere here, having a magnitude of 72. And how are we going to connect the 2 points? This will be connected again by a second degree curvature because of this a line. And because the slope here, the magnitude here is 0, we expect that the slope at 88.2 will also be 0, hence making this a curvature to be concave in the downward direction. So here is our curvature directed in the downward direction. Then the next point that we shall be having is the moment at C, which is at this point. And this can be taken as the moment at B plus the area of the shear diagram between B and C. And if we're going to look at our area, the area is actually composed of two area. One area would be rectangle and the other one is an area under spandrel. And if this is to be subtracted because these are located below the neutral axis, the horizontal axis, therefore the moment as will be equal to 72 minus 18.3, representing the area of this rectangle. While this one third of 18 multiplied by 3, it will represent the area of this spandrel, a colored green in our illustration. And when we simplify, this moment will be equal to 0. And so our moment here will be equal to 0. And so when this will be drawn, connected, this will be connected by a third degree curvature. Third degree because our shear diagram is a second degree curvature. Hence, we shall expect that this will be a third degree curvature having a slope at 72, smaller than the slope at C, and therefore we shall expect that it will also be concave in the downward direction, running in this manner. And so after we have computed for the moment diagram, you will notice that the maximum moment is at point D having a magnitude of 88.2. And so from here, we can already solve for the first question. So what is our first question? Our first question is to solve for the maximum maximum flexion or bending stress. And so we're given that the maximum flexure stress is computed as mc over I. And because we have a rectangular cross section, this can be simplified to be 6m max over BD square. This is, take note, only applicable for a rectangular section. Hence, we shall be having a value of the stress equal to 6 multiplied by 88.2 kilonewton meter divided by 250, okay, divided by 400 square. Okay, because we have here a different unit, so we can convert this kilonewton meter into newton millimeter by multiplying this by 10 to the 6, because 10 to the 6 newton millimeter is equivalent to kilonewton meter. So that here kilonewton meter will cancel. Also, we shall have millimeter will cancel. What will remain is a unit of newton per square millimeter, and that unit is equivalent to a unit of megapascal. This has a value of 13.23 megapascal. So this becomes now the maximum stress, okay, which is acting at this section of the beam 4.2 meters to the right of A and at the top or at the bottom of the beam. Okay, so after that, we can now compute for the second question. Our second question is to find out for the stress at the section 3 meters to the right of A and 50 millimeters from the top of the beam. And so we shall be solving for the moment at the section 3 meters to the right of A. So when we are talking of moment 3 meters to the right of A, okay, there are several ways of computing for the moment. Maybe we can compute for the moment at this point, because when you say 3 meters, it will be the moment at this point. At this point. However, we can also consider going back to the original loading condition, because the moment that we are talking actually is the moment at this section of the beam 3 meters to the right of A. And so if we will be considering this section 3 meters to the right of A, and we isolate the left part of the exploratory section, therefore this is what we will have. Okay, so this is what we will have, and we simply consider the moment at this section of the beam. So this part of the beam would have a total loads equal to 3 multiplied by 10 and acting over a distance of 1.5 from this exploratory section. And therefore, the moment at 3 meters, we're talking of the moment here, then the moment here will be equal to 42 multiplied by 3 minus 3 multiplied by 10 multiplied by 1.5, and this gives us a value of 81 kilonewton meter. So this is now the moment at the section 3 meters to the right of A. And since we are looking for the moment at the section 3 meters to the right of A at a fiber 50 millimeter from top, so we shall solve now for its stress. We are talking of the position of the fiber, which is located somewhere here. So let us try to imagine that this is our neutral axis, and here is our fiber where we are computing for the stress. The distance of that fiber from top is 50 millimeter, and therefore, because the height of the depth of the beam is 400, and so the distance of that fiber from the neutral axis shall be equal to 150 millimeter. And if we are to solve that, substitute those value in the formula for stress having the formula equal to my over I, the moment at that section is equal to 81 kilonewton. The distance of that fiber from the neutral axis is equal to 150 millimeter, and the moments of inertia is equal to 1 over 12 kb times d cube. And so when this will be simplified, we shall be getting a stress equal to 9.11 megapascal. And so guys, sana ay nasundan ninyo yung ating explanation on the stresses in beams, and particularly the derivation of the formula, its application in solving for stress in beams that are subjected to bending moment. Muli, salamat sa inyong pagsubaybay guys sa ating discussion. Sana ay patuloy niyo ako sundan by subscribing to this channel, or if you have friends that sa tingin nyo ay mangangailangan ng ganang klase ng discussions, you may share it to them so that they may also be notified of this lecture. Once again, thank you very much for watching.